So this is an evaluation transformation where we start with a polynomial as an input, and the output is going to be a vector in R2. And the way you implement this map is to plug in 0 and then plug in 1. And that's how you make the vector in R2. So here's the example is, if we take the input 3 plus 5t plus 7t squared, that's the vector p. If we plug in 0, we get 3, and if we plug in 1, we get 15. So the output is 3 and 15. So the problem asks you to show that t is a linear transformation. You can show that t is a linear transformation by showing that it respects linear combinations, or you can find a matrix that implements the map. So we could say, this is not on the spec sheet for this particular problem, but let's find the standard matrix of the transformation. Let's find the standard matrix of the transformation. So the standard basis for P2 is 1t and t squared. And we know to find the standard matrix of t, we map the the basis vectors. So if we plug in the polynomial 1, when we plug 0 into this polynomial, we get 1, and when we plug 1 into this polynomial, we get 1. Let's find the image of t under this map. We plug 0 into this polynomial, we get 0. We plug 1 into this polynomial, we get 1. And then we map t squared. The image, we plug in 0 into this polynomial, we get 0. We plug 1 in, and we get 1. So the standard matrix of the transformation is 1, 1, 0, 1, and then 0, 1. Any questions? Okay. So if I multiply this matrix by the vector if I look at the coordinates of P, what did I miss? I missed something. Let me pause, not the video, but let me stop this for a second, because I just confused myself because I read the question and I started thinking about multiple things. If you're given P of 0 and P of 1, and to solve for P, you're looking for a polynomial such that P of 0 is 3 and P of 1 is 15. So if you wanted to do this backwards, so if you're given that T of, say, P is equal to 3, 15, you're looking for a polynomial such that P of 0 is equal to 3 and P of 1 is equal to 15. We know that this is a polynomial, say a x squared. I should use t. I should also write it in the correct order. So P is a polynomial in R2, so P of t will be c plus b times t plus a t squared. And so you're just trying to solve, plug in 0 and we get 3, and plug in 1 and we get 15. So we could solve it that way to go backwards for P. Notice that we've only got 2 pieces of information here, and we have 3 constants to solve for, so there's going to be more than one solution. All right. Any questions? Okay, so if we go back to the standard matrix thing, if I multiply this, I got 3 plus 0 plus 0. And then I've got 3 plus 5 plus 7. So I get 315. In this case, I looked at the coordinates of the matrix of the vector p, and the output was 315. So if you're given an output vector, you can use an augmented matrix to solve. So if you're given an output vector, I shouldn't be using this symbol because that usually means stopping of the video. So if we're looking for a matrix, a vector, if we're looking for a polynomial, c bt at squared, I can solve this equation, 1, 1, 0, 1, 0, 1, multiplied by the vector cba, and figure out which one comes out to 315. And that would just be a matter of solving the augmented matrix, or not solving, excuse me, of reducing the augmented matrix, 1, 1, 0, 1, 0, 1, 315. And then find the reduced row echelon form, and then get the general solution. Oops, AP equals X. But this goes back to what we talked about with linear transformations at the very beginning. If we want the matrix of a transformation, which we always want the matrix of a transformation, because we want to frame everything in this class in matrix form. We want everything in matrix form. I know it works to solve the equations with polynomials. It works to solve just by setting up with polynomials, but the point of the class is to use matrices. It's like in Calc 2. We can just use the formula for the volume of a cone to find the volume of a cone. But the point is not to find the volume of the cone. The point is to use calculus to find the volume of the cone. So the point is, we can solve these problems with polynomials, but the point of the class is to use matrices to solve for these polynomials. Any questions? How's everybody? Let's find the reduced echelon form of this matrix and see what it tells us, and see if it fits with what we know about what's going on in this problem. So I've got the matrix 1, 1, 0, 1, 0, 1. It's an augmented matrix with a 3 and a 15. I'm going to find its reduced row echelon form. It's far too close to 11 o'clock for me to solve this just by looking at it. So I'm just going to use my calculator. That's what it's there for. So 1, 0, 0, 3. 1, 1, 1, 15. So I've got 1, 0, 0, 1. Those are my pivots, and then 0, 1, because that's just going to come out the same. And then we end up with 3, 12. So we have 3 variables. So this was C, B, and A. And what we can see is that C has got to be equal to 3. And that's a basic variable. We got a pivot in C and a pivot in B. But it looks like A is a free variable. So B is equal to 12 minus A. And A is free. I shouldn't say equals. I should just say A is free. So here's what the general solution looks like. C is 3, B is 12 minus A, and A is free. The general solution looks like 3, 12, 0 plus A times 0, negative 1, 1. So any polynomial that has these coordinates will do. A was equal to 7, if A is equal to 7, then B is equal to 12, and we get 3 plus 5t plus 7t squared. And that will have P of 0 will be 3, and P of 1 will be 15. So if A equals 7, then B is equal to 12 minus 7, or 5, and P of t, 3 plus 5t plus 7t squared. We plug in 0, we get 3. We plug in 1, and we get 15. So that works. If we pick a different value of A, say A is equal to 1, then B is equal to 12 minus 1, or 11. Then the polynomial P of t should be 3 plus 11t plus t squared. So if we plug in 0 into this polynomial, we get 3. That's why this c equals 3 had to be fixed, because there's no t to change it. It can't be dependent upon the t. So 3 plus 0 is 3. Plug in 1, we get 3 plus 11 plus 1, which is still 15. So for every value of A, we get a polynomial that comes up with 3 when you evaluate it at 0, and 15 when you evaluate it at 1. To get the standard matrix, you find the columns of the standard matrix, of a transformation are the images of the basis vectors So if, oops, not double T. We have a transformation T maps, say, Rn to Rm, and this has a basis then the standard matrix, or then the matrix of the transformation, is the image of the basis vectors under the transformation. Map the basis vectors. The words are, the columns of the standard matrix of a linear transformation are the images of the basis vectors. Start off by learning the words. I try to say sentences like that when we're defining things. I try to say those sentences over and over again because they become like the lyrics to a song. We only learn the lyrics to a song because we hear them over and over again. Once we have the lyrics, then we get to think about what those lyrics mean and use them. The columns of a standard matrix of a linear transformation are the images of the basis vectors. For P2, so if T maps P2 to R2, doesn't matter what, the standard basis for P2 is 1t and t squared. So the matrix for matrix of T will be the image of 1. Oops, not commas, these are columns. And then the image of T, and then the image of T squared. Because the images of the basis vectors are the columns of the standard matrix. The images of the basis vectors are the columns of the standard matrix. The images of the basis vectors are the columns of the standard matrix. The images of the basis vectors are the columns of the standard matrix. The columns of the standard matrix are the images of the basis vectors. Any questions? Cool, I'm gonna pause the video here.